After 3 class sessions of trying to get our data in order, it's finally in order, so that's great. So we're going to be able to explore this today. So one of the things that several of you have asked about or expressed interest in at different parts in the class are some of our environmental justice components part of climate change, right? And so some folks did that for some of their presentations, but not everybody did. So we wanted to have our last data assessment give everybody an opportunity to explore that stuff. And so we'll get to the look at the data set in a second, but just wanted to give you guys some background. So when you look back at these variables that you've been typing the data in, you hopefully have a little more context. So we'll just spend a few minutes here just making sure everybody's up to speed. So this is timely, of course. So this is just today. The Senate voted to overturn yet another air protection rule that, in this case, one for power plants that essentially says if you had a toxic release, the power plant needs to monitor that particular toxin or a suite of toxins, in perpetuity. And the Senate just said, nope, that's fine. If you release some stuff, that's okay. We'll just assume you're okay. So this is again part of the everything we're hearing about. And Professor Spees was just saying that there's also we're beginning to remove species from the endangered species list today. So this is a very relevant thing. Yeah. Okay, so let's give a brief background on air quality. So that's not something we typically talk about in a lot of our classes. So the legal foundation, the regulatory world is built around the Clean Air Act, one of our foundational environmental protection laws that came in the so-called golden age of environmental laws in the wake of the stuff in the 60s and early 70s. And absolutely the Clean Air Act is a super important law. It's been really key in getting us to have a lot cleaner air in much of the country. Unfortunately, with climate change and some other things, we're beginning to slip and slide backwards on some of our progress. But nevertheless, that's what does it. And the key thing for us today is that the Clean Air Act tells the federal EPA to set what are known as National Ambient Air Quality Standards, or AQSs, for pollutants that we are concerned about that cause harm. There's 2 basic types of stuff. There's primary standards and secondary standards. The primary standards are about you, and particularly they're aimed at more vulnerable populations. So populations either because of their physical condition or their behaviors make them more potentially susceptible to inhaled pollutants and toxins. So think little kids or think people that have asthma, that kind of stuff. And then the secondary standards are to protect general welfare, including things like view sheds. So I'll just be real clear and say that the Clean Air Act also talks about being able to look out and see the other side of the Grand Canyon, stuff like that, right? That's an important value that this law is supposed to do. In addition to doing things like protecting non-human things, agricultural crops, etc., even structures, homes and stuff. When this was coming up, one of the issues was acid rain. And so the fact that we had a lot of these toxins in the air that either dry deposit or through rain come out of the atmosphere and land on, say, concrete and start to dissolve the concrete or what have you, that's considered a thing that's regulatable as well. Famously, a few years ago, the Supreme Court also said that CO2 is also a regulated component. That is also under direct assault, and the removal of that is well underway by the powers that be at the moment. Okay. Generally, we have these so-called pollutants of concern, or if we're talking about in regulator speak, we're talking about criteria pollutants. And so this is ozone, particulate, PM is particulate matter. So we usually talk about this as PM₁ or PM₂.₅. That's referring to particles that are the size in microns. So 2.5 is a particle that's 2.5 microns in diameter, its largest diameter. carbon monoxide, sulfur dioxide, nitrogen dioxide, although sometimes we monitor NOx, which is all of the nitrous oxides, not just dioxide, and then lead. And so we do this through setting these so-called AQSs, these air quality standards, as we mentioned. And that's going to be a health-based criteria based on peer-reviewed literature and the kind of stuff that, Professor Spies and I or Dr. Kafella, we work on, and we do a study and we find, oh, here's a problem, and that goes into the thinking and planning for the next update of the standards for stuff. And most of these are based on concentration and duration. And so hopefully when we look at the table in a few minutes, it'll make a lot more sense, all those numbers, those different columns that you were typing stuff in. And the idea is there's a threshold beyond which you see heightened risk. So we should think about these things also, just for your own understanding. You don't want to be this is the speed limit, right? This is the speed limit for the pollution. You don't want to be at that level, right? You generally want to be less than the speed limit, right? You don't want to be right on the edge every single time. So we ideally want to be below and hopefully well below these danger warning levels of stuff. Okay, we do this typically with one of two standards, a 1 hour standard and an 8 hour standard. So for the 1 hour standard, these are for things that have really acute effects. So you breathe it in and instantly, you start to have maybe some problems breathing, or your windpipe starts to close up or something like that. And that's, so acute effects, short-term exposure. So this would be things like the sulfurous compounds, carbon monoxide, which if you breathe just a little bit of it, you can start to go unconscious and stuff like that, or some of the nitrous oxides. And the goal with the 1 hour standards are to prevent immediate bad things happening. So this would be stuff like triggering people's, inducing an asthma attack in someone, and extreme events causing a heart attack in people, that kind of stuff. So that's the 1 hour standards. We set this, it's a statistical thing, right? Because remember, the air, every breath we're taking in another chunk of air, right? And sometimes it's windy, and so air can fluctuate a lot, as opposed to, say, soil temperature. If you think about something like that, a soil temperature is not going to fluctuate wildly from minute to minute, potentially. I shouldn't say wildly, but it generally won't fluctuate at all from minute to minute, right? Sort of a slow. Air can be very fast. So we use these so-called 99th or 98th percentile of the daily max over an hour. So we do the readings over the course of an hour, and then we calculate the statistics based on a rolling 1 hour period. And then for the standard, we usually average that over 3 years. So if you had one bad month or one bad week, that's not necessarily going to be horrible, but we want to look at is it frequently bad, right? So we do this over 3 years. And examples of this include the 75 part per billion sulfur standards, the 35 part per million carbon monoxide standard, and the 100 part per billion NO2 standard. And then we have the 8 hour standards. So the 8 hour standards are for things that have, that if you just breathe it right now, you're not going to suffer necessarily hardcore problems, but it's more of the chronic exposure we're worried about. So long-term, breathing it in, if you walk through a little, so on the 1 hour standards, it would be a cloud that if we walk through, you could die, or you could have really bad breathing problems. This is not like this. This is more like if you lived in the neighborhood with this day in, day out, that's going to cause the problems. And so the idea here is to protect people that have long-term exposure outside. So think kids in playgrounds, or people, say at a construction site or something of that nature. And examples of this would be stuff like the 70 part per billion ozone standard, or the 9 part per million CO standards over 8 hours. As we go forward, these standards are, I shouldn't say constantly. So this is, as with many of our regulations, trying to solve a problem, but we understand it's very hard to turn the ship once we've already, the U.S. economy, vehicles, all these things are a huge big ask to change that stuff, right? We can all say, hey, it'd be great if everybody was in electric cars and we didn't have that internal combustion pollution coming out. That'd be great. But everybody's got internal gas combustion engines right now, right? So we can't pivot on a dime. So the general approach is we break the country up into different air basins, different air pollution control districts, or called slightly something differently sometimes, but that's the idea. And those at the state level or at the sub level below the state, we look at what's going on and go, okay, your guys' table is really bad, your guys' table is not so bad, and so we create some different guidelines. And the idea is, we know we can't all be like, the North Slope of Alaska or something like that right now, but the idea is we all want everybody getting better, right? Getting better. So we started off with these standards that were fairly high, and over time, we're making them tighter and tighter. One, that's because we're getting better science and we understand, oh my gosh, even a little bit of air pollution can cause people problems over time. So one, it's the science is getting better. But two, the other thing is we basically try to give the regulatory authorities, the local folks, time to adapt. And we understand that you can't just replace all of your equipment or add scrubbers on everything instantly. So it's sort of over time, tighter standards, tighter standards, tighter standards. So for example, when we upped the particulate matter standard here in 2014, all of a sudden a ton of the country became what we call non-attainment, meaning we're not hitting the air quality standards that we've set out, right? Those different levels for different pollutants. And so in this case, this is that particulate matter 2.5. These are the smallest particles. These are the ones that get even easier to get deeper into your lungs, and so therefore potentially more problematic than bigger chunks of stuff. And what we see is when we did that, all of a sudden, of course, our area is perennially a bad spot. We have so many cars, we have so many people, all that kind of stuff. So no super surprise that sort of the greater LA area is a bad one. Something that people don't realize is the Central Valley is actually oftentimes way worse than LA. And again, that's because of the physical structure of the Central Valley. So we have like inversion layers, different atmospheric events that act as a lid on top of the air mass, and then mountain, sort of a bowl of geography around it to sort of not let that air exchange with other masses and get diluted. But have a look, also like sort of the industrial Midwest is also super red. So I think when we kicked this standard up, it became something like 70 million people suddenly were living in air that was not meeting the EPA's standard for particulate matter, right? So partly that's because things are happening, but also it's because we're tight. Mostly it's because we're tightening the standard. It is the case that things like droughts, that things like wildfires, that things like climate change and our management that we've chosen to engage in leads to more poor air. And so in our part of the world, that's mostly going to be drought-driven and wildfire-driven. Okay. Well, another tool that we have in our data set that you can explore is a tool when it first came out, a couple decades ago, I guess the first iteration, it sucked, to be totally honest. But every time we've updated it, it's gotten better and better. And currently we're on the 4th major revision of what's called the Cal Enviro Screen. And it's actually pretty good now. It actually is pretty useful. So this was begun by folks in Southern California, begun by some nonprofits, and they said, we want a tool to help explain different populations' vulnerability to different environmental stressors. And so without going into all the details here, basically it does this based on census blocks. So I had to do a little bit of magic math and you'll see that in a second. But census blocks, remember that our data was reported on zip codes, so they're not exactly the same thing. But in any event, based on that census block, the demographic data of the folks that live there, the average makeup, demographic composition of that area, and it says what's the model is based on what's the pollution burden, so the exposures that these folks get. So maybe they live next to a LAX or a big transportation corridor, something of that nature. And then there's something about the population characteristics. So are these folks typically older? Are these folks typically younger? Are these folks typically from a community that engages in work that maybe brings them more into contact with toxins and various things, right? So those things get combined together in a sophisticated way, and we end up getting a score, which is a measure of the potential pollution burden. And so if we look at our area, this is what you see. So if you turn on CalEnviroscreen, this is what you'll see for our county. And so in this case, the hotter or the warmer the color, the higher the score on CalEnviroscreen. And so how you'd interpret that is you'd say this people that live in this zone are more typically having a higher pollution burden, right? So again, that's either because of where they live or or how they behave, their demographics. It's all that stuff combined. And so we see some areas like out in the mountains are green, right? So that if folks live there, on average, they don't have a particularly elevated pollution burden. Whereas folks that are in more urban cores, next to industrial centers, things of that nature, they're going to have on average a higher score. And the score ranges from 0 to 100, with 100 being the most exposed or the highest burden people are experiencing. And it generally tracks with things like ozone and asthma and stuff like that. And so there's a lot of interest in not looking at stuff at the county level, but looking at that finer scale. So in this case, this is how we were picking some of our sites for a study that is continuing. But in this case, this is the proximity to oil and gas facilities, right? And so we're not saying that oil and gas facilities are inherently evil, but on average, oil and gas facilities tend to produce some of these precursor compounds, methane and things of that nature that can cause some issues, right? So you might look at a potential source and say, oh, hey, let's put a monitor there, or let's see what the pollution burden is there. The data that we all use, that you guys all typed in and we cleaned up last class session, is based on not our data. So our Ventura County, we are one air basin, one management district, but we're relatively small and we don't have a huge amount of data compared to these other areas. So we're not looking at Ventura County in this activity. We're looking at the greater Southern California South Coast Air Quality Management District, which is mostly LA and Orange County, but it also includes Riverside and San Bernardino. It's just, there's more data. So it's more stuff to look at, easier for you guys to create correlations and stuff like that. And so this is what we're talking about. And each of these things is one of the current active monitoring stations. Okay, so here's our data. So we'll run through it in a second, but this is all the stuff you guys compiled, so it's all ready to go for you guys to start playing with. And just a couple quick examples of the kind of stuff you did. I just made a couple really quick graphs before class, just to show you what you might want to think about. So in this case, here we have a measure of ozone, and then on this one we have visits to hospitals, visits to emergency rooms because of a respiratory distress condition. Right, so generally that's interpreted as asthma. Theoretically, it could be something else, but some people having problems breathing, right? So we don't know what triggered it. Maybe somebody had a cat and they had a reaction. They went to so we don't know it was because they were breathing outdoor air, but we're just using that as a proxy. And so in this case, we have the range, and then we can say, hey, is there any elevation? You can do stuff like that. Here's an example of adult asthma visits. Again, visits to the local hospital emergency rooms, and environmental justice. And now in this case, because we have one score, so the CalEnviroscreen doesn't vary by year, right? We just have the best current estimate. So because of that, we have a lot of things that have the same values. So maybe a better way to do that would be something like this, right? So to calculate a mean and variation, right? And so I've just sort of twisted that last graph on its side. And so again, in this case, we have the CalEnviroscreen. Recall, as we go to 100, that's a heavier pollution burden. We think that population is being exposed to on average. And then this is, how much time or how frequently we go to the hospital, right? And so, this certainly looks like, as we go through time, it looks like there's a tendency to go up. There's also some interesting things here where most stuff seems to be following this general increase curve. But then we have a couple things like this site and this site that has, like really elevated. So what's going on there? Maybe there are other factors going on to explain that. So you guys can explore that. As a reminder from the stuff we've always been training you guys, we've just been doing this, right? So for the last couple days, we've just been going through all these processes as a group, right? QA, QC, double checking, confirming, all that kind of stuff. And so I'm going to finish walking you guys through the orientation because we were so busy focused on typing in the data. We maybe didn't get a good orientation. So I'm going to walk you guys real quickly before we wrap this up through the variables at the top so you can make sure you understand the structure. And remember how we do this, right? Let's not forget what we learned in the first couple weeks of class. First, let's say, what's the big picture? What's the biggest value? What's the smallest value? What's the average value? All that kind of stuff. And then, make some quick and dirty graphs like I just did. Like, hey, how does X compare to Y? Is it sort of generally going up? Is it not really affected? What's going on? And then once we get there, then we can start to talk about doing the more sophisticated graphing, the more sophisticated, maybe some adjustment to the data or something of that nature. And again, we've been processing the whole last few class sessions. So I thought this would take like half a class session. It took 3. So that's my bad. But you guys get the idea. Does this make sense? Okay. The additional thing before I show you guys, we jump to the data and I show you guys, what we're going to do this time, rather than just give you all the data and say run away and go look at it individually, is we want you guys to sign up for a couple exploratory looks that we want you guys to do in the next little bit here. So here's these pollutants, here's ozone, and maybe I'm interested in ozone and the mean score of the CalEnviro So I'm going to put my name in that box. And then, somebody else, Kale's going to maybe do ozone and percentile bends or something like that, right? And so rather than all of you sort of looking at all the possibilities, because there's a lot of possibilities here, we're going to sort of divide and conquer. So everybody's going to take a little quick look, see if there's anything there. Maybe something looks interesting, maybe not. And then we'll report out to each other as to which things look like they might be interesting. Sound good? Okay, cool. Okay, so here's the data set. And let me all just explain it before you type anything. Just everybody look up here for a second. So right now, I've kept everything with all the embedded formula. So in case you wanted to see how we generated this. You can simply copy this, and when you make your copy, you can just paste it, copy and paste and eliminate all the formulas. That'll make the sheet run a lot faster and a lot quicker. But again, wanted to make sure you guys saw everything. Essentially, we have some zip codes down here. The adult refers to the adult hospital visits with asthma. Child for the child hospital visits. And then CalEnviro. So these all come from different data sources than the ones you were typing in, right? So I use the XLOOKUP function in these different. Then the other approach was to because the zip code is not going to be unique, right? So the zip code is going to be the zip code and the year. So we created a special variable which does make it unique. So okay, now it's only this zip code, only this year. And then that's the key term we use as the data translator, as the Rosetta Stone, right? So from there, we can go and jump to these other CalEnviro, adult, child, whatever, and pull the data in. So that's how I aligned all this data up. So I didn't go line by line typing in all the CalEnviro data, right? We have our data here, have something to translate, put the data sheet on another tab, and then told the program to go grab the right variables and put them in. Cool? Good? Okay, so let's take a quick look at the variables, and then we'll turn you guys loose. Again, we're going, I should also say, so the 2023 data and the which is our most recent data year, and then the oldest data year, which is 2012, we don't have the hospital visits from either of those sites. So we do have the air quality stuff if you wanted to look at that and some of the demographics, but we don't have the hospital visits. So just realize that that's not an error of the coding. We just didn't have data there. Okay, so we have the receptor area, we have the AQS, and you now know that's Air Quality Standard Station. That's a unique term that the EPA designates. So all the air monitoring stations around the country, they all have a unique term, or unique number, excuse me. And then this is the coding, city, zip code, Latin lawn. If you don't have to make a map. If somebody wanted to make a map, I guess you could. And then we get into CalEnviroscreen. So again, CalEnviroscreen is based on census tract. All the pollution data is collected based on zip code. So in some cases, the census tract is basically the same as a zip code. But in many cases, like in Los Angeles, the zip code is much larger than a given census tract. So in some of our sites, we have like 20 different census tracts in one zip code. So there's no perfect way to figure that out, right? At least without sort of doing all the calculations. So what we've done is, if I click on this, you'll see this is whatever the max value, so whatever the most vulnerable index number is that's what that is of as many census tracts that are in the area. And then this one is the next one is the minimum. So this would be the worst possible case. This is the best possible case. And then this is just a simple arithmetic average of all those things. So if there's 3, it's the average of 3. If there's 10, it's the average of 10, what have you. And then a very popular thing in this world is to use percentiles, right? To use bins. So this is a score, so this is a number. And then this percentile is how does it compare to all the other jurisdictions in the state of California? Is it in the top 100%? Is it in the top 1%? What have you? Yeah, okay. And then on this last one, I made and so again, this is the percentile based on the max, percentile based on the min, percentile based on the average. And then this guy over here is just a simple percentile if you want to use that. So in this case, 90 refers to the 85 to 90, right? So it's the top of the percentile bin in 5% steps. Are you with me? Okay. Then if we keep going, so somebody clicked off that so we can see this a little bit better. Okay, so if we keep going, then this is for adults, and adults are folks older than 18. The child is younger than 18. This is a category. And so this is the number of there's none in this one, but so this is the number of visits to the emergency room. And then this one is the adjusted rate. So this adjusted rate is because some of our areas have a lot of people, right? Some have fewer people. So the adjusted is standardized per 10,000 people. What we think, taking demography and stuff into account. So that's like the standardized version. So sort of more apples to apples for every jurisdiction. How frequently, or how many emergency department visits based on respiratory distress. And again, adult, child, we talked about that. Okay, then as we start to click around here, you guys can just see this. So carbon monoxide, days of data, sometimes sensors go down, right? So in this one was operating correctly for 363 days of the year. In this case, this one at this station operated for 342 stations and so on and so forth. This guy was operating every single day of the year. And then this one is the max 1 hour concentration of, in this case, carbon monoxide. And as we go across, what you're going to see is, right? So you'll see some different standards, particularly around things like ozone. Ozone is one of our success stories. Ozone's been getting better in most of the places around the world, particularly here in Ventura County, South Coast, LA, et cetera. So we've improved a lot with our ozone exposure, say over the last 20 years, 30 years. I should also say, just to make sure we're on the same page, this is ground level ozone. We like the ozone at the top of the stratosphere. It blocks UV radiation and stuff like that, ultraviolet radiation. We don't like it down here. Down here, it screws with our lungs. It makes rubber crumble. It causes all kinds of, and it's also associated with other pollutants and stuff. So all this ozone, we're talking about ozone that we don't want, that we don't like. And so what you'll see is there's some different standards. So these are all ozone. Here's the old federal standard, which was more than 0.12 parts per million. And as we scroll over to the right, you get the current one, which is 0.07 parts per million, et cetera. So as you scroll through, you can see all these different things. So in some cases, it's just one standard, but in these more popularly, or I should say, substances of concern, we've been updating those standards. So they've reported out all these different numbers for you, so it's nice and standardized. Cool? William?
So what does it mean then when there's empty ones? Do those stations not collect data?
Yes.
Oh, okay.
So the question is, so what happens when it's a blank cell? So for example, we have 6, well, we're about to get a 7th, but we have 6 year-round, 24 hours a day, 365 monitoring stations here in the county of Ventura to monitor air. One in Ojai, one out in Oxnard area, one out towards Simi. One in they're sprinkled around. They do not all monitor everything, right? So they monitor the pollutants we are most concerned with. So for us, the biggest concerns are particulate matter and ozone. So all of them will do particulate matter, all of them will do ozone. They don't all do nitrous oxide, for example. And that's a cost thing, right? That we just don't have the resources to do everything all over everywhere. It would be great, but we don't have that ability. And the idea is, hey, if we have this pollutant under control, let's put our resources onto the thing that we're really actively trying to improve. Does that make sense? Okay, so a couple things just to remember. This is the raw data. You guys are going to make a copy and then move it to your desktop, move it to your own drive. Do not leave a copy in this. Do not edit the master file. Everybody will be very angry with you, right? Don't delete that or mess with it. And again, recall that right now there's a bunch of formula in here. So once you download it, I would select the whole thing, copy it, and then paste special as values. So you can just get rid of all those formula, right? And go from there. And then the last one I'll just say is, remember, there are a few notes, and we just typed all the notes in raw. So sometimes there's an asterisk. Mostly that's because the sensor went down for a week or something like that. So instead of reporting the number, it's like the number with a caveat. So you can decide individually how you want to handle that. So you might want to just keep the number 2 and delete the asterisk and just say, I'm just going to assume this is good. Or you might want to go and delete that whole variable because it's not, there's some question about it. There's something that's different than the other ones, but that's up to you. That's your choice. But do realize that there are some letter and some non-numeric characters in here. So if you just start trying to do automatic calculations, you're probably going to get errors. So once you decide what you're going to do, clean up the data set first. And I don't know if Professor Spies has any suggestions.
And it might be good to have two. So when you start your next sheet, right, you have the master data set that you're copying over. You should probably have another tab that's just the clean version that you're going to work in, right? So that way, if you have to go back and be like, oh shoot, I'm not sure if I remove this or remove the asterisk, whatever, you can just go to the next tab and look at the raw master data. But then the other one's the clean version that you could remove asterisks or remove data or whatever, and that would be the one that you do your graphs and everything in.
I would also just add, just for your own, making sure we're on the same page, so Professor Spies and I have been finding data for you guys. We did reef check stuff. We did Gobi data, right? All that kind of stuff. It can be hard to find some good, and you guys were hunting for your own data sets, right? When we were doing our own stuff. While biologic or abiotic data are relatively easy to find, at least some sense about it, finding this kind of data, which relates a physical parameter to some social justice, environmental justice thing, they're not as abundant, right? So that's why we had to spend several days creating this. There isn't just like hey, let me have the master file of whatever, right? And that's just because this is a lot harder to do than just sort of, I mean, there's challenges with monitoring the air. I'm not trying to say it's simple, but doing this is another step, another additional complication. So that's why we had to make it for ourselves.
This is what I meant by that, is when you download the data. I just